This presentation gives my general thoughts about what can be learned from past severe accidents in nuclear reactors. Before starting out, look at the Daniel Kahneman quote. During this talk, you may conclude that some of our predecessors made crazy mistakes. These things look crazy to us, mainly because we've benefited from their mistakes. Also, I'll talk about some of the events, but I only have time to touch on a few main points. The events are really more interesting than I can convey in a short talk. During the Fukushima-Daiichi accident in 2011, I was a member of the IAEA engineering team, charged with giving the bosses our daily best estimates of the plant's conditions. That led me to start thinking about how severe accidents happen. IAEA defines severe accidents as an accident more severe than a design basis accident and involving significant core degradation. It is one of 5 fundamental plant states that they define as shown in the table. Note that what IAEA calls design extension conditions are typically called beyond design basis accidents in the US. After I retired from IAEA in 2013, I began to put some effort into this just for my own amusement. But on my first trip back to Vienna, a colleague asked for a summary of severe accidents for their nuclear knowledge management program. I liked the idea, but now I had to take it more seriously. Later, IAEA asked me to develop video presentations about some of the events. So far, I've made videos for TMI, Chernobyl, Fukushima-Daiichi, and HTRE-3. I spoke about this work at an ANS meeting in 2015. Joe Nazier from EPRI saw that talk and asked me to write a report on lessons learned for instrumentation, control, and human system interfaces. From here on out, I'll use the acronyms INC and HSI. So now I have 3 products: accident summaries and videos for students, and an EPRI report for practicing engineers. At the end of this video, I'll tell you how to get these products. My first step was to make a list of severe accidents. I took account of earlier work and then went looking on the internet and in libraries for other events and accident reports. The internet has some crazy stuff, but nothing made it on this list unless I found a credible source that acknowledged significant fuel damage was involved. In most cases, I was able to obtain accident reports or secondary documents based upon the original reports. I found 19 events. The plants include 4 Generation 2 LWRs, 7 other power reactors, 2 isotope production reactors, and 6 test or research reactors, including NRX at Chalk River, which had the first severe accident in 1952. There might still be events that I haven't found. Just having this list shows that severe accidents have been more common than we think. The red line shows the cumulative number of severe accidents by reactor year. The shape of this curve shows that the industry is improving. Currently, the conditional wisdom is that the frequency of severe accidents should be about 10 to the minus 7 per reactor year. But if we consider only Gen 2 LWRs and decide that Fukushima-Daiichi was 1 event, not 3, the frequency of severe accidents through 2017 is slightly less than 10 to the minus 4 per reactor year. This is a much higher number than most people believe. I conclude from this that we should expect further severe accidents, and it will be some time before severe accident frequency will be as low as 10 to the minus 7 per reactor year. A cursory look at the loss of hulls from both aircraft and large cargo ships indicates that the frequency of those events may also be around 10 to the minus 4 per hull year. These industries have been around a lot longer than nuclear power. We've had cargo ships for a few thousand years. Could it be that 10 to the minus 4 per unit year is some kind of lower limit for severe accidents in complex systems? That would be a great question to investigate. After studying these accidents, I came to believe that severe accidents are black swans. The term black swan in this context was coined by Nassim Nicholas Taleb. Black swan was a common expression in 16th century London to describe impossibility, deriving from the Old World presumption that all swans must be white. The point is that for Europeans, all known swans were white until they discovered black swans in Australia. Taleb uses the term black swans for events that are hard to predict, have serious consequences, and that are obvious in retrospect. I believe that the pattern for severe accidents is that unknown or unrecognized hazards lay dormant until some trigger causes the latent hazards to become real hazards and creates an event that can't be brought under control before serious core damage occurs. It's hard to predict an event when the conditions that cause it aren't recognized. You can't model what you don't understand. Taleb points out that someone predicting an event may not disqualify it from being a black swan. What's important is that those affected failed to foresee their fate. For example, he notes that at Thanksgiving, the turkey is always surprised. Next, I'll give you a simple example of this model, an event that happened at Chapelcross Unit 2 in the UK. Chapelcross 2 was one of 8 similar gas-cooled reactors that used natural uranium fuel assemblies of the Magnox type. Calder Hall 1, the first reactor in this series, was the first nuclear power plant to generate industrial quantities of electricity in 1956. Plants in this series continued in service until 2004. In the early days, these plants had the dual role of producing plutonium and electricity. A little bit of background will help you understand the event. Fuel assemblies were loaded and unloaded through the tubes shown on the left. The tubes passed through the reactor vessel head, and most of these tubes serviced 16 fuel channels, so a fuel assembly had to be manipulated a bit to get it into the correct fuel channel. The fuel channels shown on the right were columns of graphite bricks. In Chapelcross 2, graphite sleeves were inserted into the channels to isolate the graphite bricks from the reactor coolant flow so that the graphite bricks would operate at a higher temperature, high enough to prevent an accumulation of Wigner energy. These sleeves sometimes became dislodged or broke during removal or insertion of fuel assemblies. It wasn't possible to detect such damage during fuel load. Fuel failure was detected by a sampling system that monitored each group of 16 fuel channels. This picture shows some of the sample tubes. Gas from the tubes was sampled sequentially and sent to remote radiation detectors. Selection, transport, sampling, and measurement delays meant that for each group of 16 channels, fission product measurements could only be updated no faster than every 90 seconds. In 1964, experimental fuel assemblies were installed in several channels. In one case, part of the graphite sleeve was damaged either before or during loading of the experimental fuel. The broken parts fell into the coolant flow path, restricting coolant flow, but during plant operations, there was still enough flow to cool the fuel. The affected channel would have run hot, but the damaged channel was one that didn't have fuel channel outlet temperature sensors, so operators were blind to the problem. 3 years later, fuel elements of a new design replaced most of the fuel, but the fuel in the damaged channel was left in the reactor. Engineers knew that the new fuel would increase the reactor coolant temperature by about 100 degrees C, but this was still 200 degrees C below the experimental fuel's design temperature. When the reactor was brought up to above 200 megawatt thermal, the coolant flow in the damaged channel was no longer sufficient to cool the fuel assemblies, and fuel began to melt. Fuel failure was detected by the fission product monitoring system, but system response time and a procedural requirement to independently confirm the problem before scramming the plant delayed the reactor trip by 1 or 2 minutes. In that time, 6 fuel elements melted. This was a pretty minor event, but I picked it to show you how a problem can lay dormant for quite some time, maybe even forever, without causing trouble until just the right set of conditions trigger an event. But severe accidents aren't always so simple. Consider the TMI accident. The reactor fuel melted because of a stuck-open pressurizer power-operated relief valve and failure to provide coolant makeup sufficient to replace the water lost through the PORV. I'll give you a short synopsis of how this event transpired. The green text in this slide denote things that went right. The event was initiated by isolation of a condenser polisher caused by a poor maintenance procedure. In Unit 1, an isolated polisher would have been automatically bypassed so as not to cause a reactor trip. Unit 2 didn't have this feature, so a turbine trip and a reactor trip occurred. Safety systems worked as expected and started high-pressure safety injection. When it came time for the operators to take action, a design error caused the control room indicator to show that the stuck-open PORV was closed. A lack of information about similar events, a desire to avoid a solid reactor coolant system, and poor procedures supported the operator's belief that they were responding to a normal reactor trip. They reduced the reactor coolant makeup rate as required by the procedure for a normal trip, when in fact they were confronting a loss of coolant. It's likely that they could have quickly recovered from this decision, except that the plant had been operating for some time with a PORV that was leaking more than allowed by the plant's license. Because of this, the high PORV tailpipe temperatures that also indicated a stuck-open PORV looked normal to the operators. Useful secondary displays that could have helped were not easily accessible, and poor training in thermodynamic principles and small break LOCA response didn't help them to diagnose the situation. As things got worse, the core exit temperatures would have identified the problem, but temperatures were displayed considerably behind real time, and outlet temperatures only a bit higher than normal were shown as question marks. Reactor pressure water level indication would have clearly shown the problem, but in those days, US PWRs didn't have RPV level indication. It was 2.5 hours before operators started to understand the plant's real state. By that time, it was very difficult to recover from the event, and more problems raised their head. Removing almost any one of the red things above would have prevented the accident. Note that most all of the equipment involved worked as designed, and where failures occurred, the equipment was operated outside of its design envelope. This was typical of all the events. The severe accidents were generally not caused by random failures of equipment. We pay great attention to preventing such failures and designing so that failures can be tolerated. This has most certainly limited the frequency of design basis accidents. The issues leading to severe accidents can be attributed to unrecognized hazards, like the failure to recognize that a high point loca behaved differently than a design basis loca for TMI. Plant design issues like the addition of fragile fuel assembly sleeves at Chapelcross. INC design issues like the PORV position indication, showing the demanded position of the valve, not the actual position of the PORV at TMI. Operating procedure issues like the instruction to delay reactor trip on high fission product activity until confirmatory information was available at Chapelcross, or maintenance issues like the poor condensate polisher procedure at TMI2. In retrospect, it's hard to identify the root causes of these issues, but the usual suspects are inadequate safety analysis, incorrect equipment specification, or inadequate information given to those who prepare training and procedures. These were subtle issues that became important only when an unexpected set of operating conditions were encountered. Always more than one issue was needed to cause a severe accident. Severe accidents always involved bypass of multiple independent layers of defense in depth. You may be familiar with defense in depth as a series of fission product barriers: fuel pellets, fuel clad, reactor coolant system, containment, and low population zones. But there's a system-level defense in depth concept too that is described by the International Nuclear Safety Advisory Group, or INSAC. INSAC is a committee of highly experienced graybeards who advise the IAEA on safety issues. INSAC describes defense in depth as a series of systems, each independent from the other, and each backing up the preceding system. Rows 3, 4, and 5 of this table describe the levels of defense in depth in the INSAC model. Reading right to left, the layers are 1. Prevent abnormal operation and failure through conservative design and quality in construction and operation. 2. Control anticipated operational occurrences using protection systems and other surveillance features. 3. Control accidents within design basis allowances through engineered safety features and accident procedures. 4. Control severe accident plant conditions through complementary measures and severe accident management guidelines, or SAMGs. 5. Mitigate radiological consequences of release during severe accidents through off-site response measures such as sheltering in place or evacuation. Each of these layers will, if successful, protect the public. I'm sure you can't read the table very well, but it's worth a look sometime. Here's a chart illustrating how the independent levels of defense in depth were bypassed in the 19 severe accidents. The boxes on the top identify the 5 defense in depth levels, and the yellow arrows indicate the conditions that caused bypass of each level of defense in depth. In every case, some condition bypassed multiple levels. According to the INSAC model, this shouldn't happen. Severe accidents happen when unrecognized dependencies cause the defense in depth model to break down. To help you understand the basis of my claim, I'll give you the Twitter version of a few events. As a result of inadequate natural phenomena design bases at Fukushima-Daiichi, a large tsunami disabled nearly all plant systems. The lack of severe accident management procedures and associated practice hampered operators' attempts to restore core cooling and defend containment integrity. Eventually, fuel melt and partial containment failure occurred in all three plants. Operators at Chernobyl were unaware of several design hazards, and ignoring allowed operating limits, the operators brought the plant to a condition where low coolant void fraction initiated a power increase. Recognizing the problem, the operators scrammed the reactor, unaware that in the existing plant condition, the scram would insert reactivity, and rod insertion initiated a reactivity accident. The St. Laurent II design didn't include loose parts monitoring. An in-vessel component came loose and eventually blocked some fuel assemblies, initiating fuel melt. Fission product detectors sensed the problem, but the reactor trip set point was too high to trip the reactor in time to prevent significant fuel damage. During online fuel loading at St. Laurent A1, interlocks prevented the operator from loading several fuel elements. He overrode the interlocks and loaded what he thought was fuel. Actually, what he loaded were flow restrictors, and fuel began to melt. The set points for the high fission product activity reactor trip were too high, and significant fuel damage occurred before the reactor trip. Fermi 1 didn't have a loose parts monitoring system. As a last-minute safety improvement during construction, metal plates were added to the bottom of the reactor vessel to act as a core catcher. During operation, bolts holding the plate corroded, and some plates came loose. Operators noted odd axial temperature distributions at the tops of the fuel assemblies, but while they were trying to diagnose this problem, two plates floated up to the top of the coolant inlet plenum and blocked flow through three fuel assemblies. SL1 was designed such that rapidly removing the reactor's center control rod could cause criticality. Designers believed that the operators couldn't lift that rod fast enough or high enough to cause a criticality. During a maintenance activity, an operator lifted the center rod and proved the designers wrong. Within microseconds, a steam explosion launched the reactor vessel about 10 feet out of the operating deck. All three operators in the reactor building were killed. At the sodium reactor experiment, petroleum coolant for reactor coolant pumps leaked into the reactor vessel. Some of the petroleum coolant combined with some of the sodium reactor coolant to form a tar-like substance. During plant operation, the tar clogged coolant channels, initiating fuel damage. Before much damage occurred, a series of negative period trips occurred, indicating that something odd was happening in the core. But operators reset the trips and restarted the reactor because they believed the trip instrumentation was unreliable. The reactor operated in severe accident conditions for 11 days before the operators recognized that they had a problem. During startup testing of HTRE-3, an untested automatic power control system was used. For this test, ion chambers used for the power control and reactor trip system were positioned too close to the fuel, and the ion chamber high voltage power supplies were set too low. During startup, the combination of high gamma environment for the detectors and low detector current due to the low voltage caused the detectors to begin working in the counts range rather than in the linear range. When that happened, indicated power decreased as the actual power increased. The automatic power control system continued to bring power up to about 400% of the intended maximum power. At that point, fuel relocation and scram on a backup reactor trip ended the event. During an activity to remove Wigner energy from the graphite in the core at Windscale Unit 1, plant power levels were controlled based upon fuel temperatures. But operators had left the fuel thermocouples in locations away from the planned hotspots in the core. They couldn't know how hot were the hottest fuel elements. Two sets of fission product detectors couldn't detect the situation because in one system, core outlet gas was not aligned to pass by the detectors, and in the other system, thermal expansion of the structures intended to scan detectors behind the fuel channel outlets bound up because of very high temperatures in the reactor outlet plenum. Considerable fuel caught fire. The unrecognized dependencies are common cause failures, but they are not common cause failures of equipment. They are common cause failures of the mind. It should be a reminder to always check your intellectual blind spots. Most severe accidents had minimal effect on the surrounding area. Accidents with local consequences mainly affected only the plant site. The list above is sorted more or less in the order of the degree of fuel melt. 11 of the plants in the lower two categories were eventually returned to service. It's interesting that the last 4 accidents were the worst. One possible reason is that most of the other accidents involved low-power reactors. But this doesn't explain everything because the 2 San Laurent units and 105K West operated at thermal power levels that were about 80% of the Fukushima-Daiichi units. Severe accidents haven't caused the expected levels of public radiation exposure. At Windscale and Fukushima, the mitigative actions kept public exposure within acceptable limits. The actions taken at Chernobyl were not as successful, but still, radiological consequences to the public were lower than expected. There's no evidence that any member of the public has suffered deterministic effects of radiation exposure from a reactor accident, and only at Chernobyl is there evidence of the public suffering stochastic effects. The United Nations Scientific Committee on the Effects of Atomic Radiation concluded that the Chernobyl event resulted in about 6,000 additional thyroid cancers in Ukraine and Belarus, and that these 6,000 cancers caused approximately 15 fatalities. This is not good, but it is significantly below what was expected from such a horrendous event. For years, our prime directive has been to spare our neighbors from harmful effects of radiation exposure. With the exception of Chernobyl, we've succeeded. But radiation exposure wasn't the only serious consequence of the accidents at Fukushima-Daiichi and Chernobyl. More than 500,000 people were displaced from their homes for a substantial period of time. At the end of 2017, about 55,000 evacuees from the Fukushima-Daiichi accident were still living away from home. I found no such data for Ukraine, Belarus, and Russia, but it is known that some Chernobyl evacuees decided on their own to move back into the no-go zone. Belarus has just recently started opening up some areas for resettlement. About 50 people died during the evacuation at Fukushima-Daiichi. The deaths that I know about were hospital patients who could not be immediately moved. They were left behind with a skeleton staff with the intent that they would be evacuated a few days later. It took longer than expected to move them to a location where they could be properly cared for. Depression and post-traumatic stress syndrome were common amongst the affected and even the unaffected at both sites. A 2013 survey of Fukushima evacuees determined that most were still living in evacuation shelters. Nearly half considered themselves socially disabled due to traumatic symptoms, and nearly all thought that they or their offspring would suffer health effects from radiation exposure, when the real number is probably zero. A 2016 study of Fukushima-Daiichi determined that mortality rates amongst the elderly in the area increased by a factor of 2 to 3 during the 4 months after the accident. It's clear to me our prime directive to not irradiate our neighbors is insufficient. The prime directive must also include never making our neighbors move from their homes. From the EPRI work, I found that INC or HSI issues contributed to all but one event. I concluded that the INC and HSI contributions could be grouped into 5 categories. INC functions that were needed to deal with the accident didn't exist. Existing INC functions that would have helped to deal with the accident were not in service, usually for reasons other than failure. Existing INC functions that would have helped deal with the accident didn't have the required performance characteristics. The operators could not see or could not understand displays that would have allowed them to better deal with the accident, or some life cycle activity, such as incorrect calibration or improper assembly of a fuel element, contributed to the accident. Note that the large number of INC and HSI contributions reflect the fact that multiple INC contributions were involved in most of the accidents. So to recap, while many of the events considered are old, I think their lessons are still relevant today. Today, a generous estimate is that the frequency of severe accidents is about 10 to the minus 4 per reactor year. We should expect future events. Severe accidents appear to be black swans. Unknowns led to inadequate design, training, or procedures. Severe accidents were generally not caused by equipment failures, but by the fact that plant design, procedures, or training did not account for the unknowns. Severe accidents involve bypass of multiple levels of defense in depth. Such bypasses occur when discounted. Our unknown hazards introduce unexpected dependencies between levels of defense in depth. And we've done a good job of protecting our neighbors from radiation exposure. But we must do better to avoid moving them away from their homes when such accidents occur. This work has been very interesting for me, and I don't think I've fully wrung out yet all that can be learned. It impressed upon me the wild ways that things can go wrong. Most such accidents are extremely complex, and the causes cut across multiple disciplines. We'll probably never be able to fully eliminate the kinds of errors involved, but the study is a clear reminder that if you work on things nuclear, you must avoid falling into the somebody else's problem field. The nuclear power business involves many disciplines, but no matter what our background, we are all in the end plant people. If you wish to read more about the events, the EPRI report is free and public at the above URL. If you want the IAEA accident summaries or videos, I prefer that you get them from IAEA. I want them to know that they're being used. If the IAEA doesn't come through, let me know. The following slides give a short bibliography to support some of my statements and identify the main accident reports that I used. About 500 documents are in the full set of references and bibliography. I'll run these slides through fast, but you can stop them if you want to read anything.